We were looking at the linear phase domain model of the clock and data recovery circuit without the forwarded clock. The model looks like this. This is the incremental phase of the data, and you have the phase detector gain. Which gives the average output current ICP. That goes through a series RC combination, and then you have the incremental model of the phase model of the VCO, which provides the output clock. Now we saw that the loop gain is this could be written as right. This is a convenient form. The first one is the integrator response, which gives you a unity gain frequency of omega u, and the second part is the 0. Okay. Now we want to set omega z to be sufficiently smaller than omega u for good phase margin. In fact, we will see that other performance parameters also force this to be substantially smaller than omega u. Okay. Now, what did we find? The transfer function of the output phase to the input data phase. This will be 1 plus s by omega z okay. So now if you assume that omega z is much smaller than omega u, okay, what are the approximate roots of the denominator, the poles of the system? Omega u and omega z. So this can be approximated by 1 plus s by omega z, 1 plus s by omega u. Okay. But I have to say that, I mean, obviously now you see that the s term, when you expand it out, the s square term is exact using this approximation, but the s term will be 1 by omega z plus 1 by omega u, whereas it should have been only 1 by omega z. Okay. So obviously if omega u is much larger than omega z, it's a good enough approximation. But it turns out that this pole here, you will have some pole P1 and some other pole P2. P2 will be approximately equal to omega u, and P1 will be more than omega z. If you calculate it, that's what it comes out to be. Okay. P1 will be at a higher frequency than omega z. So first of all, what will the shape look like now? So let me plot everything on the same plot. This is the magnitude of L and omega. The magnitude of L looks like that. This is omega u and that is omega z. Now from this expression here, assuming omega z much smaller than omega u, using the approximation, what will we get this to be? Phi ck by phi d? What will it be? So this will be just a first order transfer function, and this is what you expect anyway, because this is L and L by 1 plus L would be this is the approximate phi ck by phi d, and it has a bandwidth of omega u radians per second. So that means that any input jitter of less than this frequency will be followed by the clock and data recovery circuit. Now if you look into the details a little bit, like I said, this pole will be at a slightly higher frequency than the 0. Okay. So what will happen in that case? How will that change this plot? As per now, what will happen? It will 3 dB down where? Omega? No, that is okay. That is just a Bode approximation thing. I am saying we made this approximation that this polynomial has two roots at omega z and omega u, right? But what I am saying is this first pole here is not at omega z, but it's at some frequency greater than omega z. Okay, what will happen as a consequence of that? Yes, Ajay, what is it? Why? No, I am looking for qualitative changes in the plot that I drew. Yeah, of course it will change, but what? So if P1 was exactly equal to omega z, what would happen? So I have 1 plus s by omega z, 1 plus s by P1, 1 plus s by P2. And for now, let me say that P2 equals omega u, just to avoid any confusion. If P1 was exactly equal to omega z, what would happen? You'll have pole zero cancellation and you will have just a first order roll off. Now I am saying P1 is not exactly equal to omega z, but slightly more than omega z. So what happens? Yeah. So what happens is that in reality you will have something like this. I mean, again, these are Bode plots which approximate everything using straight line segments. When poles and zeros are very far apart from each other, it is okay. Otherwise you will see some smooth variation. But anyway, I will nonetheless use that. Let's say the pole is here, then it will do that, and then at some point here it will start doing that. Okay. So in reality there will be some peaking. That is, the pole will not be exactly at the same place as the 0 and there will be peaking. Now as omega z increases, as omega z approaches omega u, this peaking also increases. Okay. Is this okay? I mean, there are two separate things that happen. So we have 1 plus s by omega z, 1 plus s by omega z plus s square by omega z omega u. Okay. So this is the transfer function. Let me take only the denominator part of this. Now this denominator, this will have complex conjugate poles if omega z is more than omega u by 4. Okay, you can calculate the condition from the quadratic. Also, what is the damping factor or the quality factor of this? What will be the quality factor? Square root of what by what? Omega z by omega u, and the damping factor will be. So also you see that if omega z becomes more than half of omega u, the quality factor will be more than square root of 1 over square root of 2. What happens in that case? What is special about this 1 over square root of 2? Huh? No, that is not. Yeah, so this factor itself, as omega z gets closer to omega u, first the poles become complex conjugate, and then after that, if the quality factor rises beyond 1 over square root of 2, this factor itself will do this. There will be some peaking. On top of it, you add the 0, there will be a lot more peaking. Okay. So there will be, as omega z increases, first of all there will be peaking because of 0, and if it becomes too close to omega u, you can also have peaking because of essentially the system becoming sufficiently underdamped, that is quality factor rising beyond 1 over square root of 2. Okay. So anyway, so as omega z increases, there will be peaking, and that, what does peaking mean? This is a ratio of output phase to input phase. So what does it mean? What does it mean to have peaking here? At that frequency? Yeah, so what does it mean? Is this a clock and data recovery system? What is that? What does it mean? Clock is advanced? No. What is the meaning of a transfer function? What are we plotting here? Huh? Yeah, so basically if the data is jittering around, the clock will jitter around even more than the input data. That's what it means. I mean, if at the frequencies where you have peaking, right? If data is jittering around at that frequency, the data edges are jittering around, then the clock edges will jitter around by even more. Okay. So instead of kind of following the data jitter or even completely removing the jitter, this is actually increasing the jitter. Okay. And in some kind of systems, this can be a big problem. Okay. Especially, I mean, there are some standards and some systems where you have a transmitter and then you have a receiver where you recover the data and the clock, and you use the recovered clock to retransmit the data, and that goes some distance. Again, you have one more clock and data recovery circuit which will recover that and do this. So essentially, this is a like really long haul transmission system, and this clock is recovered and regenerated many times. Now, if you have peaking here, even if you have a small peaking in one of the CDRs, after it goes through some 20 stages, the peaking can become really substantial. So in such cases, there is a very stringent constraint on peaking. It cannot be more than a small fraction of a dB, right? You shouldn't have peaking at all. But in some other cases, it may not matter as much. Okay. But this transfer function will always have peaking. Okay, that is the characteristic. I mean, if you have a polynomial of this type, I mean, ratio of polynomials 1 plus s by omega z, denominator you have the same 1 plus s by omega z plus some s square term. This will always have peaking. If omega z is like much smaller than omega u, which means that if the system is heavily overdamped, then the peaking will be small. Okay. And you generally see that most of these clock and data recovery circuits are designed with a large damping factor. Whereas in an op-amp feedback circuit, you may design for damping factor near 1 or half or something. This one will be designed for a damping factor of 5 or some large damping factor. Otherwise, you get peaking because of this 0. Okay. Any questions here? So this is the loop gain, and this is pi ck by pi d. Okay. Now what will this look like? The other transfer function, pi ck by pi vco. What was this? This was s square by omega u omega z divided by 1 plus s by omega z s square by omega u omega z. So if you plot this on the same axis, what will that look like? Please sketch that on the same axis. I mean, please try to draw both transfer functions on the same scale, right? Pi ck by pi d and pi ck by pi vco. You expect it to be complementary to this, right? So again, if I approximate the denominator as 1 plus s by omega z, 1 plus s by omega u, the numerator can also be separated s by omega z, s by omega u. Okay? Each of this is a high pass transfer function with a high frequency gain of 1. Okay? So the first term here looks like this, where this is omega z. The second term here looks like this, where this is omega u. What will the product look like? So let me draw the slopes a little, let me draw the curves a little shallower. What will the product look like? So this part will be 1, okay, and here it will be like that, and here it will rise at plus 40 dB per decade, plus 20 and on. Okay. This is 5 CK by 5 VCO. As you expect, the low frequency phase noise of the VCO would be very strongly suppressed, right? And in the middle, maybe a little less so. But at very high frequencies, there is no suppression at all, because as the VCO output phase is jittering around, this feedback doesn't have any strength in it to counter that. Okay? So basically, there is nothing that happens. So you have a gain of 1 for the high frequency part. Is it okay? Any questions here? Fine. So we can also quickly look at the other transfer functions. I think it's, yeah. So what will these look like? 5 CK by VNR and 5 CK by INCP. This is the same as that, right? Except for this scaling factor. Okay, it's also a low pass transfer function. What about this one? Yeah, so what kind of transfer function is that? So these transfer functions have some dimensions. So I'll plot them on a different axis. So phi clock by phi INCP. What does that look like? It will have this. This is omega z, omega u. To a first approximation, it's a low pass filter with a corner frequency of omega u. But we know that it will also have some peaking. And this value, how much is this? 1 by density factor times ICP by 2 pi. So the density factor becomes smaller, this gain becomes larger. Okay? And the other one, phi CK by VNR, what does that look like? Yeah. So with the way we have it, we have a big separation between omega z and omega u, right? So this whole thing, this factor can be, we have s by omega z divided by, again denominator I can approximate it in the same way. This time it's a product of a high pass function and a low pass function. So it's a product of the high pass part has a corner of omega z and the low pass part has a corner of omega u. Okay? So the overall transfer function will have this sort of broad band pass type structure. So that, I mean, it will have a different dimension, right? So this factor will be the gain. Okay, which I think we said can also be written as this number, right? 1 by density factor times ICPR by 2 pi. It's the same thing. Is it okay? So now, knowing the noise from each of the components, right? You may have some noise in the data that you have to know, then you can find the contribution to the output jitter. And similarly, phase noise of the VCO you will have to know. We will look at the nature of the phase noise of the VCO just after this. And then the resistor noise is white, and the charge pump noise, it will consist of, it will of course have a white noise, but it may also have some flicker noise. So you have to multiply the spectral densities appropriately and find the output spectral density, output phase noise, or the variance by integrating it. If you want to integrate it, you have to integrate the magnitude squared of this, but in the first assignment you have already calculated those integrals, right? So those will come in handy. Okay. So for instance, what will be the phase noise due to R, due to the loop filter resistor alone? How much will that be? So this is the transfer function, right? So the magnitude squared of that appears. We will have 1 by density factor ICPR by 2 pi, this whole thing square, and then you have the transfer function this has to be evaluated at J2 pi f, and you have to take the magnitude squared of that, right? And what else? What do you have? Huh? Integrate. No, this is the spectral density. This is the phase noise spectral density. So what is it? What about the resistor spectral density? What is that? So it is 2 kTr. This phase noise is one side of a two-sided spectral density, right? So it is 2 kTr. Okay. The integrated jitter due to this is so much, right? So now you see that basically if I remove this here and this goes away with that, okay. And that goes with that. So this is okay actually. Sorry. Okay. This is fine, right? So the integrated jitter is inversely proportional to ICP. Okay. So if you want to reduce the integrated jitter due to R, you have to increase the charge pump current. This is basically the general lesson anytime. When you have thermal noise, if you want to reduce it, you have to increase the power dissipation. Now, of course, if you increase ICP and you want to keep other loop parameters the same, like omega u and so on, you have to reduce R, okay, or you have to change KVCO. Similarly, if you, this is also proportional to KVCO, so to get low jitter, low phase noise due to R, you have to use a VCO with a smaller gain. That actually becomes more and more difficult with shrinking supplies, right? Especially ring oscillators have very large KVCO values, and now you are designing ring oscillators with supply voltages less than a volt, okay? So, and it also makes sense, if you have a small amount of voltage available and you want to cover a certain frequency, KVCO will be larger, but that comes with this penalty that you will have a larger jitter due to larger jitter generated in the circuit, okay. Similarly, you can evaluate it from the charge pump current, then also you will get it to be inversely proportional to ICP, okay. And of course, it's inversely proportional to transition density, because if you have too few transitions, you don't have as much correction, and then you have a lot more jitter. Okay. So you can evaluate this integral from this. Similarly, you can evaluate the integral from the charge pump current and whatever else. Is this fine? So a common calculation that is required is you design your circuit, and then you can decide the bandwidth and so on. But then how much current to use, what resistance value to use, what capacitance value to use. So for that you have to evaluate the jitter. Okay. So let's go back to performance metrics of the clock and data recovery circuit. So we had jitter tolerance, right, which is usually abbreviated to JTOL. So what you do here is you vary the, you deliberately input data with a sinusoidal jitter and you vary its frequency. At every frequency, you go on increasing the jitter until the bit error rate goes above a certain value. And in our case, we can't calculate the bit error rate. We will say that when the phase deviation, when phi ck goes beyond a certain value. Okay. We just take phi ck for calculations. Then what is, there is this thing known as jitter transfer, JTRAN. This is how much of the input jitter gets transferred to the output. You will specify this by knowing the input jitter, knowing the transfer function, and finding out the output jitter spectral density or the variance and so on. Okay. This is essentially the transfer function, phi ck by phi d, right? And then there is jitter generation. This is, if you apply a clean, jitter free input data, the output clock will still have jitter. Okay. This is because of various reasons. One is of course the random noise in the charge pump as well as in the loop filter resistor, also the random phase noise of the VCO. That is one thing. And then a clock and data recovery circuit can have some systematic jitter generation. This is especially true for the bang phase detector that we will see. Okay. So this is essentially the amount of jitter generated by, amount of jitter generated when the input data is jitter free. Okay. So please quickly, I think jitter transfer we have already plotted, right? Phi ck by phi d. So can you plot jitter tolerance? Let's assume that, yeah, I made a mistake here. This is not phi ck. What is of relevance is phi d minus phi ck, right? That is, the jitter of clock with respect to data should be within certain limits, okay, to have a certain BER. It's not just the jitter of the clock alone, right? So let's say that for jitter tolerance calculations, phi d minus phi ck should be less than some phi p, okay? So then you plot the jitter transfer and the jitter tolerance. Jitter transfer we have already plotted, jitter transfer function, that is okay. Now jitter tolerance will have units of either radians, or you can express that in unit intervals and so on. So what will that look like? What will jitter tolerance look like? You just have to, I mean, we did this for the case without the forwarded clock, right? Sorry, with the forwarded clock, right? We've already calculated this, isn't it? I mean, if you go back to a few classes. Yeah, so these were the transfer functions, and this is the jitter tolerance, right? So now you do this for the case without the forwarded clock. Okay. All you have to do is apply that condition, that's all. That phi d minus phi ck should be less than some value phi p, which will be some fraction of 2 pi. What's that? Yeah, so you find out what that should be, right? I want the constraint phi d minus phi ck to be less than phi p, right? So by the way, what is jitter tolerance? It is a plot of phi d versus frequency such that phi d minus phi ck is less than phi p. You understand? That's what we plotted, right? The amount of jitter in the input data phi d such that phi d minus phi ck is less than phi p. Okay? So from the transfer function, from the jitter transfer function, you can also calculate this. Yeah, that's what, yeah. So at low frequencies, you can have a lot of jitter in the data. Essentially, this is the jitter tolerance curve, and then as long as your jitter, the input data jitter is less than that, it's fine. Right, just follow whatever we did for the case with the forwarded clock. we want phi d minus phi ck to be less than something. I don't know what I called it earlier, delta phi max or phi p or something. Delta phi max. So this basically says that right, or phi d should be less than delta phi max divided by 1 minus phi ck by phi d. And how much is this? This 1 minus phi ck by phi d will be s square by omega u omega z by 1 plus s by omega z plus s square by omega u omega z. Okay. So this will be delta phi max times 1 plus s by omega z plus s square by omega u omega z by s square by omega u omega z. Okay. So this again we can factor it and see. Okay. So essentially these are the inverse of the curves that we multiplied for getting the transfer function from the VCO, right? The first one will be something like this with the corner being omega z. The second one will be something like that with the corner being omega u. The product will be the jitter tolerance. Okay. So if I plot jitter tolerance on this curve, this is a transfer function. This JTRAN is a transfer function. This jitter tolerance is jitter, right? So at very high frequencies, it will be equal to what? The delta phi max that you can tolerate. This makes sense because what happens is if the input data is jittering around at very high frequencies, that jitter is not transferred to the clock at all. So the clock is fixed. So the maximum you can tolerate is whatever maximum deviation you can have for that bit error rate. And then it increases like that at 20 dB per decade as you reduce the frequency, and then it goes like that. Okay. So this is the jitter tolerance curve, and if you look at any paper describing clock and data recovery circuit with a VCO, it is like this. Okay. Now depending on the values of omega z and omega u and so on, I said there can be peaking. If omega z becomes close to omega u, there can be more peaking here, and similarly there can be a dip in this also. So for instance, it could be that somewhere around the corner jitter tolerance actually reduces below phi max. Okay. Why does this happen intuitively? How can it be that jitter tolerance is smaller than phi max? What is phi max? That is the amount of movement in the clock from the center of the data so that the bit error rate increases beyond a certain value. Why does this happen? If the transfer function is such that, let's say the input data jitters like that and the clock jitters in the opposite direction, right? Clock is supposed to follow the data, but it could be that in such cases the clock is actually going in the opposite direction. So that means that the clock minus data is more than the data jitter itself. So then the amount of input jitter has to be smaller than what you can tolerate. So this can actually go below delta phi max also in some conditions. Okay. Is this fine? So these are the three parameters that you always see with clock and reported for a clock and data recovery circuit. And jitter generation is, the random jitter generation we have seen. So essentially you will have, this is the output jitter or output phase noise, let's say, and integrating this you will get the jitter. So this will be the spectral density of charge pump noise times the corresponding transfer function magnitude square. Okay. This will be 2 times L if you take the single sided spectral densities, or maybe let me say S phi of f, and then you can appropriately calculate the phase noise. plus the spectral density of R, which is the loop filter resistor, times phi ck by, this was just INCP, this is VNR square, plus the phase noise of the VCO. Maybe I'll change this to phase noise, this is fine. Phase noise of the VCO times phi ck by pi n VCO square. So this is the jitter that is generated. This is the spectral density, and integrating this you will get the jitter. And because this is phase noise, you have to use basically two-sided spectral densities here. Okay. That is, if it's a resistor, you have to use 2 kTr, and if it's a MOS noise, you have to use 4/3 kTgm and so on. Okay. And integrating this, you will get the jitter generated, the variance, or you can calculate the standard deviation of the jitter generated. Is this okay? So by now, I mean, you should be able to kind of choose the bandwidth of the, or at least choose the component values if you are asked to design the clock and data recovery circuit for a given bandwidth. What bandwidth would you choose? I mean, would you choose a very high bandwidth or low bandwidth in a CDR? You should choose a high bandwidth so that for whatever input jitter you have, you do follow the clock follows the data. But there is a trade-off, because a high bandwidth means this part moves to the right, so you will have higher jitter tolerance, but also the jitter gets transferred to the output clock over a wider bandwidth. So that may not be desirable in some cases. When you use especially there are cases where you take the recovered clock from the clock and data recovery circuit, and without doing anything more to it, you use that to regenerate data and send it out. So in that case, the quality of that clock is also important. The jitter of that clock is also important. So then there can be a trade-off. On top of it, there will be some practical constraints, as you will see in the future assignments, which will prevent you from having a very large jitter tolerance. And especially with bang-bang phase detector, which is what is most popularly used, there is one more component of jitter generation that is very important. It is there in the linear phase detector also. Besides the random jitter generation, you will have some, because of the way the jitter phase detector operates, there is some systematic part to it. Okay. So that can become very large if the bandwidth is large. Okay. So we'll look at all those things in the next few classes.